So this is the last video in the chapter about curve fitting. And in particular, we're going to talk about nonlinear regression. In nonlinear regression, the model function y is a nonlinear function of x and of the parameters a1, a2, up to am. So given a set of n data points of the form xi, yi with I between 1 and n, curve fitting starts by assuming a model y of x with m parameters. These parameters can be obtained by minimizing the sum of the squares of the differences as shown here, where we have the sum of the model prediction of the data minus the actual data squared, and then the sum of all of that gives us s. To find the parameters of the model that would minimize s, m equations of the following form are solved. So we take the partial derivative of s with respect to each of the coefficients, and in the expression shown here, we're taking the derivative with respect to ak, which is the kth coefficient, and that has the form shown here. And then we set this equal to 0, and that gives us m equations in m unknowns that allows us to solve for those unknown coefficients that would minimize s. Now, since y of x is nonlinear in the coefficients, the m equations formed are also nonlinear and can only be solved using a nonlinear equation solver method, such as the Newton-Raphson method that we discussed in Chapter 6. In this chapter, we will use the built-in MATLAB function nlinfit, which can be called with the syntax as shown here. So I'm using the variable coefs to represent a vector containing all the coefficients, and then r is the other output here, where r is a vector containing the residuals or the delta i's. And it's important that it's not the square of the residuals. So if we want to use the square of the residuals, then we have to square the quantities in r. And then the inputs to the function are x and y, which are the vectors containing the data points. Model is the model function, which can be defined in another m file and called using the function handle. And then beta 0 is a vector of initial guesses for the unknown coefficients. So the algorithm that nlinfit uses requires an initial guess for our resulting coefficients. So you can put those in as a vector. So let's look at an example. The following data represents the yield strength sigma y and the plastic strain epsilon p obtained from uniaxial experiments, where the first variable is the plastic strain, as shown here, and the second variable is the corresponding yield strength, shown here. We want to find the best fit for the data, assuming the relationship follows the form sigma y is equal to k times epsilon p to the power of n, where k and n are the unknown parameters. While this model can be linearized as described in section 9.4, we will use the nonlinear regression techniques described here. So this is the MATLAB code to define the model. So I've defined it as a function in its own m file, and I'm calling that function plastic, and it accepts the a, which is the vector of coefficients, and x, which is the data points that I want to evaluate my function at. So a1 is equal to k, and a2 is equal to n. So I just write it returns y, which is equal to a1 times x to the power of a2, or k times epsilon p to the power of n. Then I can call nlinfit with the defined model and an initial guess of k is equal to 100 and n is equal to 0. And that is shown here. So I'm using my output variables are my coefs and r. I call the function nlinfit with my input is my x and y, which are defined earlier in the function. And then this is how I'm calling the model using the function handle, indicating that both a and x are passed into it as inputs. And then init is my initial values, my initial guess for both k and n. And then I can calculate the r squared using this output r. So r gives me the residuals, and I want to take the sum of the squared residuals to find my residual sum of squares, and then the sum of y squared is the denominator in my expression, and then r squared is just equal to 1 minus sr over st. So this is the output from the MATLAB script showing the model parameters k as 506.635 and n is 0.0988163 with an r squared of 0.9999918. And this is a plot showing the original data along with the model fit. So the best fit model is that sigma y, or my yield strength, is equal to 506.635 times epsilon to the power of 0.0988163. We can look at another example. So again, for plastic materials, Armstrong and Frederick proposed the model shown below to describe how a quantity called the center of yield surface, changes with the increase in the plastic strain. So if alpha is the center of the yield surface and epsilon p is the plastic strain, then the model has the form shown here. So alpha is equal to c times 1 minus e to the power of gamma epsilon p. So if we have this data given here as epsilon p and alpha, we can find the values of c and gamma for the best fit to the experimental data. And unlike the previous question, this model cannot be linearized, so we must use the nonlinear regression techniques. So again, we can define the model in its own M file that accepts a and x, where a is the vector of coefficients and x are the values that we want to evaluate at, so in this case the epsilon p. And then we can call this nlinfit with the defined model along with an initial guess, and here I'm just using an initial guess of c and gamma are both equal to 1. So again, the syntax is the same as it was before, as shown here. So here my function is called Armstrong, and I'm calling it with the function handle here. And I calculate r squared in exactly the same way I did for the previous question. And this is the output from the model. So you can see the model parameters c and gamma given here, along with the r squared of 0.992751. And you can see the original data points along with the model fit. So the best fit model for this data is that alpha is equal to 15.5624 times 1 minus e to the power of negative 94.3835 epsilon p.